Hello students, in this video we are going to see rotations in AVL tree. As you all know, AVL tree is a self-balancing tree. Always height of the AVL tree will be a balanced one. That is, its left branch and right branch will be a balanced one in its height. Uh, because when you are having the imbalanced tree, it will be increasing the searching cost a lot. By balancing the tree, we can somewhat reducing the searching complexity. So this motivation behind the balancing the binary search trees, and AVL tree is one such balanced binary tree. So in order to get that balance, we'll be using the rotation concepts in AVL tree. There are four kind of rotations: LL rotation, RR rotation, LR rotation, and RL rotation in AVL trees. First we can look at the LL rotation. LL rotation, when this condition will occur, means when you are adding a new node to the left branch of the critical node, then LL rotation condition will occur. The solution is we have to do one right rotation. Okay. The thing is, the left branch of the tree is overloaded. By doing right rotation, we are balancing the tree. So this is what we are doing in LL rotation. Let us see with an example. So let me add three nodes. Okay. So first I am having the value 4. Okay, the root node is 4, and here it is 3, and here it is 2. So now looking at the balancing of this tree, let me form the tree structure. So 3 is the left child of 4 and 2 is the left child of 3. Then we'll be adding the balancing factor. The balancing factor of 4 is 2, because the height of the left tree is 2, 1, 2, minus the height of the right subtree of 4 is 0. There is no right child to 4, so 0. 2 minus 0, it will be 2. In the similar way, the balancing factor for 3 will be 1 minus 0. There is one left branch for 3 and there is no right branch for 3, so 1 minus 0, it will be 1. And the balancing factor for 2 is 0. There is no left child, no left branch, also there is no right branch for 2, so its balancing factor will be 2. Now according to AVL tree concept, the balancing factor can be minus 1, 0 or 1. So in the case of node 2, it is not a problem, the balancing factor is 0. In the case of node 3, again there is no problem because the balancing factor is 1. But in the case of 4, the balancing factor is 2. Now this 4 is called as a critical node. Node 4 is critical node. Critical node means the node which is having the imbalanced factor. Okay. Now why this imbalance occurs? Why this imbalance occurs means, when we are adding the node 3 to the left of 4, there is no problem because the balancing factor of 4 would be 1 and balancing factor of 3 would be 0. But when I have added node 2, the balancing factor of 3 becomes 1, the balancing factor of 4 becomes 2. So it is because of this addition of 2 the imbalance occurs. So where the 2 is added? To the left branch, okay, to the left branch of 4. In the left branch, again to the left branch of 3. Okay, so it is a purely left skewed tree. Okay, if I taking from 4, the imbalance occurred because of the addition of new node to the left subtree of the critical node. So this is the meaning. Now how to avoid this imbalance. Okay, it's nothing, just move this 4 to the right of 3. Okay, just move this 4 to the right of 3. Okay, otherwise in right rotation we will be telling means the entire block will be moving on right rotation, so that 3 becomes the root node, 2 becomes the left child, and 4 becomes the right child. I'll be drawing the new. Okay, so terms of okay, in this way I have to rotate right rotation. Okay, so after right rotation, so 3 will become the root, 2 will be the left child, and 4 will become the right child of 3. Okay, so like this we are balancing the tree by using AVL rotation. Okay, now coming to RR rotation. I'll be creating this AVL rotation. Now RR rotation. When RR rotation will occur means when you are adding a new node to the right subtree of the right subtree of the critical node. The solution is by doing one left rotation we can avoid the imbalance in the tree. So we can see the example for this like previous. So this can be 5, and this node value can be 6, and this can be 7. Okay, so 5, 6, 7. It is a right skewed tree. Only we are having the node in the right branch of 5. Now I think you would have understood. 7 is added to the right branch of right subtree of, again right subtree of 5. Okay, so this is why we are calling it as RR rotation. The solution is we have to do one left rotation. Now which is the critical node, 7, 6 or 5? Yes, you are right, 5 is the critical node because the balancing factor of 7 would be 0. The balancing factor of 6 will be minus 1. The height of left subtree minus height of right subtree. So 0 minus 1, it is minus 1. And what is the balancing factor of 5? What is the height of left subtree of 5? 0. Minus what is the right height of 5? It is 2. Okay, so 0 minus 2, it will be minus 2. So again here 5 is the balancing, is called the critical node, and we have to balance it. So now if you are doing one uh, left to rotate, okay, if you're doing one left to rotate in this way we have to move the nodes. Okay, we got to move the nodes in this way. So if you're moving the nodes in this way, you just see. So 6 will become the root, 5 will become the left tree of 6, left subtree of 6, and 7 will be the as usual right of 6. Now this is the balanced tree. The balancing factor of 5 and 7 will be 0, and the balancing factor of 6 also will be 0, since the height of the left subtree and height of the right subtree is same. So this is RR rotation. Now we can go for LR rotation. LR rotation, just look at the definition. Inserting a node to the right subtree of the left subtree of the critical node. Okay, right subtree of the left subtree of the critical node. So let us take an example. So already this is the root node. Okay, the value of the root node, let it be 5. I'm adding another node. The value of the another node be 4. Okay. I'm adding another node. The value of this will be, you can make it as 3. Here we can make it as 4. Okay. Now where 4 is added, 4 is added to the right subtree. Okay, right subtree of 3, and again 3 is the left subtree of 5. So this is the meaning of this: right subtree of left subtree of the critical node. Okay, to the critical node it is left subtree, and for 3 it is a right subtree. Okay, now the solution is we got to do one left rotate and we got to do one right rotate. Okay, so first, in which direction we got to move? We got to rotate the node in the left direction. Okay, okay, when you are moving this in left, uh, so 5 will be as it is. So 5 will be here. Here, when I'm doing one left rotate, 4 will become the place of 3, and 3 will become the child of left child of 4. Okay, and again we have to do one right rotation, so that is bending. So right rotation means in this direction. Okay, we got to move the node. If you're moving the node, so 4 will become the root, 3 will be as it is, and here 5 will be node. So now the tree is a balanced tree. It happened because of LR. Okay, one left rotation and one right rotation. The last case is RL rotation. The RL rotation is just the reverse of LR rotation. To the left subtree of the right subtree of the critical node, when you are adding a new node, RL rotation will occur. And what is the solution? Just reverse of LR. The solution is first do right rotation. First do right rotation plus do left rotation. For this also we can see the example. Previous thing is LR rotation. Now we are going to see RL rotation. the value be 7. Again I'm adding a new node. The value can be 9. Since 9 is greater than 7, I'm adding to the right of 7. Then again I'm adding a new value, so that is 8. So I'm adding 8 here. Now the tree is balanced or unbalanced? Yeah, sure, it is unbalanced, because the balancing factor of 7 will be -2. The balancing factor of other 9 and 8, 9 will be 1 and 8 will be 0. Okay, so now this 8 is added to the left subtree of 9, and again 9 falls under the right subtree of 7. So we are calling it as a oral rotation. So what is the solution for oral rotation? First do one right shift. Okay, first we got to do one right shift. Okay, so when I right shifting this, okay, you see what happens. So 7 will be in the place as it is, then 8 will be moved to this, to the ninth position, that is this is being shifted. 8 is coming here, then 9 will be coming here. So this will be 8, and here you will be having 9. 7, 8, 9. So only we have done right shift. Again left shift is remaining. So again if you are doing left shift of this, okay, so this will be the resultant. 8 will become the root. 7 will be the left child of 8. 9 will be the right child of 8. So this happens because of right or left shift. It happens because of left shift. Okay, it happens because of left shift. So by using these rotations, we are balancing the tree in the AVL. So this balancing should happen whenever you are inserting a new node. The high and the balancing factors should not be any other values other than -1, 0 and 1. There is no concept like accepting all the input, then we'll be doing the balancing. Whenever you're accepting the value one by one, the balancing should happen immediately. Then only the nodes will be placed in the right position. Okay, thank you.